presenting a very short presentation.
The broadcast is now starting. All attendees are in listen-only mode.
I've just been told the broadcast is silence. And then we had Ian from Microchip. For a quick break. And then Noah on the technologies and architectures. And then in the afternoon, we had oh, no, that's going the wrong way. That's going the wrong way. And we're going to start backwards if we go backwards. Oh, no. Yeah. And you're going to sneak preview of all this. Oh.
We're not going to control this presentation mode.
Hey, you got Ben? Ah. Right. Okay, and then we're back in the afternoon. So we have Patrick. We're finishing at 1. I'll do a quick closing remark. We've got some lunch coming. Yeah, there's some lunch coming. 2 o'clock. There's not a tour of the full building. I think really it's just around. Be a short tour. Short tour.
Yes.
And how did that will take? Okay, how long? Okay. And obviously you need to be here. That won't be available for the. Okay. So there is a fire alarm test at 10 o'clock. You just sit tight. You just sit tight at 10 o'clock. You need to be escorted to the toilet. There is Wi-Fi. No.
Anyone who's like that.
Okay. Okay. You use Wi-Fi now fully. Then yeah, put your mobile phone to silent. And we'll move to our first speaker. Go to the afternoon. Okay, Ben, thank you.
Right, I'll try and balance this so that people in the room can hear me, people on the broadcast can hear me, but hopefully someone will shout if someone's saying they can't see me. Flip on, I'll just try and say next slide. I'm Ben, I work here on site at Leonard. I'm going to take you through hopefully a relatively short piece on model-based design for FPGAs with Matt Anderson. Just jump in the next slide. With an overview of what I'm going to hopefully talk through, set the background a little bit, take you through our current workflow with the tool set, take you through some of the design options for our modeling implementation, run through a few areas, for example, development of our tools in our workflow at the moment, and maybe offer some advice again on how to get started something for yourself. Jumping straight into the background stuff, model-based design or model-driven engineering, if you don't know the terms, really it's the practice using a model to analyze, define behavior of some sort of system, be it a real-world system or something we're trying to design. Model-based design considers around using model objects of some sort. That's left a little bit vague, but an object that is a model, and we use that kind of continuously throughout design lifecycle. The reason we adopted it at Leonardo is to try and reduce some of the points of failure in traditional design flows. So paper-based design flow will write requirements documents or description documents to define behavior that happens between design teams and implementation teams. Trying to increase cross-discipline collaboration and provide a sort of more common environment to do design activities from start to end and test as well. We've adopted MATLAB and Simulink from the MathWorks as our main tool set for model-based design. I think most people are probably familiar with what MATLAB is, at least as a programming language for mathematical operations, for prototyping algorithms, that sort of thing. Simulink is the tool that ships with that, which is a graphical programming analysis of systems. MATLAB and simulators toolset support kind of all aspects that we're interested in model-based design, but they also have extensive code generation capabilities, so that's really powerful for trying to target FPGAs. We've been involved in model-based design one way or another for over 10 years now, I think, on site here. The tools are constantly evolving, so we continue to adapt the workflow as we need, but it's a relatively mature process we've got now. So, and we're using those tools across multiple. Can you hit the next slide for me, Andrew? No. One more. Yeah, just a little screen grab from the web for those of you who aren't as familiar with Simulink, and more people are probably familiar with MATLAB. This is a little preview because it's set to see hopefully for some of the things I'll talk about. This is a screenshot of Simulink. You can see different components there represented on the canvas. Data routing around that model is obvious, and each of those components might have some functionality within the defined behaviors, things like that. So that's hopefully sets the background for what I'll talk about with our workflow. You not get forward another couple, Andrew. So we'll dive straight into it. This is an overview of what our workflow for getting from a system model down to hardware looks like with this tool set. The sort of left to right flow across the slide there, starting with system models, and then moving through a few stages where we kind of elaborate and add details to get towards the code generation process to then allow us to get that behavior running on hardware and test and verify it. I'm going to take you through each of these stages and try and give you an idea of what that looks like with the tool set we're using. We'll start with system modeling on the left, if you're not getting on this slide. Yes, okay, perfect. System modeling, so really we're using Simulink and MATLAB code as a combination here. This is an idea of what that might look like. So typically we're running multiple Simulink models as a stack, a hierarchy, to define a complete picture of something that we're trying to design towards. So shown along the top here, I've got a top level test harness wrapping around a kind of top level of our system, highlighted in orange. Within that system, there might be multiple components, shown in the middle there, 3 in this simple example. And we may be looking inside one of those, highlighted in purple there. We've got some lower level functionality. Bottom picture here is a graph of a kind of dependency analyzer tool, and it shows a kind of hierarchy of models that you're trying to execute. And that shows maybe more typical examples. So we might have a top level test bench that's wrapping around an overall system model that's instantiating lots of components within that. So there might be sensor models, there might be models for processing chain, lower level algorithm models, full kind of hierarchy of things that we execute and test it together. Typically for our workflow, we're interested in something that's down a few levels of hierarchy. So we're interested in looking at one algorithm and thinking about it. If we go on another slide. So when we've selected an algorithm from that hierarchy, we want to run through this workflow. The process really is to kind of add detail to get us towards compatibility with code generation tools. So normally the first stage of that is to do some fixed point modeling with a system model that's normally defined as some sort of floating point. Add fixed point details, model and test that behavior, and then add any further implementation specific details. So the obvious one to highlight is if we're doing some image processing, we might move from processing frame by frame to pixel by pixel operation from that to hardware. These are shown as kind of 2 stages, but sometimes they can be combined in the same model depending on the algorithm. The idea is to have a Simulink model which part of the feature coder, which is Simulink and MATLAB's built-in code generation functionality, which is VHDL very well. If you hit the next slide, there's a little example of what that might look like as we work with the tools. So there's a Simulink diagram here, fixed point data types written all over it, and it implements some functionality that's not too critical for what we're talking about. One of the blocks is highlighted there, a multiplier. and you can see on the right-hand side an example of code generation report. So if you generate code from that diagram, you can see it's generated FPGA, and we've got some traceability across to see what the generated code from that highlighted block is. So this is a good example of kind of the sort of cyclic process you'd be going through at this stage: modeling behavior, generating code, making sure it looks like what you'd expect or what you want, applying different optimizations, and working towards something after the code. We knock on, and we'll go and look at the next step. So you've got code generated. You want to test that code is functional, so we can go through the configuration process. Using a tool called HPL Verifier, which is another part of MATLAB, and that runs with industry standard simulators, so process object requests. Working on that slide. Show just a quick example. So we've got top left-hand corner here. There's a kind of auto-generated test harness coming straight out of the simulate tool. That instantiates your code generation model, showing the subsystem in the middle. Below that, you've got a simulation block, which under the hood is going to compile up your generated VHDL, pull up your chosen simulator. So I think model is showing here. With the source model. The generated test harness there is initially simulation is checked against the reference model to make sure the behavioral matches. So that can give you great confidence that your generated code is functionally correct from the model. And if we move on to the next slide, the next step is typically then to try and move towards hardware. So we're actually back in the code generation tools for this. Normally we want to get our code into some downstream vendor tools. For me, that's normally getting into the Vivado. So again, quick idea of what that looks like. Simulink has built-in graphical workflow for getting your generated code packaged in the IP core, support for applying all sorts of different optimizations to shape that code for either cooperate optimizations or resource sharing, that sort of thing, depending on what you're trying to do with it. There's also some control over the interface. So you see the screenshot here, an example of tying the simulated model's top-level inputs and outputs to different interface options. So either external ports and the generated VHDL component, or to an auto-generated AXI for memory maps, AXI buses. If you're not familiar with them, it's just an internal bus that a lot of vendors adopted as their kind of internal bus standard. So the tools can generate you AXI for memory map buses to implement registers. You can see there's a few inputs being mapped onto addresses within the register space. All the tools can handle sort of streaming interfaces and things like that as well. And then there is an option to do this programmatically, shown on the right-hand side of the slide there as well, and you can export from the graphical flow out to scripts, so that once you've got a sort of stable set of options, you can have a one-click repeatable build set up. And that will get you out to your vendor tools with a piece of IP. If you go on to the next slide, once you've got that, we probably want to move on to some hardware text. So again, we can fall back on the HPL Verify tools, or we've also got some in-house tooling developed over the years for running on some of our target hardware for actual projects, some of the processes we've got in the labs here. But MATLAB out of the box supports quite a lot of the standard development cards from Xilinx and the other end. You can go on to the next slide, quick little idea of what this is looking like. There's a lot going on in this, but I'll try and walk through it. That kind of orange block on the right-hand side there is a block diagram of what we're trying to aim for. So some sort of generated IP core running on FPGA. It's normally got some accessible registers for control states, feeding data in that sort of thing. And MATLAB can instantiate that in an FPGA build with an active bus master that can run over JTAG, for example, and control straight from that. So you can run it live in the same sort of environment as you can for the rest of the models. Slightly more complex example shown on the bottom left-hand side here. This is where we've taken our IP core and we've integrated it with a larger design. So we might have a skeleton design or even a real implementation that we've got running on some hardware already, and we want to drop our newly generated IP core in that and map it into our existing AXI infrastructure. So it's tied into the external memory interfaces, that sort of thing. Again, we can use the same Axie bus master IP that comes from the MathWorks to allow access to that core and all the other external memory as well, straight from that over JTAG, U6, or Ethernet interface. And if you're familiar with Vivado, the top picture there shows a screenshot of the Vivado block diagram with the Axie bus master highlighted in orange there. So you can see it just kind of sits on the active connecting way with Silence, Axie bus master, JTAG, IP forward. And that gives you very powerful control to run hardware logic testing kind of in situ. So within your hardware, within a design as the rest of your functionality or interface management. So if you want to run with a connected sensor that you're relying on a data feed from, you can do that. We jump to the next slide. Underpinning all of this is a unit test framework. So this is primarily an in-house developed framework that we've got for deriving unit test data from the system model stack that I showed right at the start of this workflow. In combination with a tool from Simulated Test Manager. If you bring up the next slide, we'll have a look at what that looks like. The left-hand side here shows Simulated Test Manager. So that's a tool from MathWorks. It's a kind of graphical way of creating, defining, and running tests. So either kind of tests that you might create ad hoc, or you can set these up as a kind of formal regression test that might be regularly run against models. And what our unit test framework does is allow you to specify a component in your hierarchy of system models. It instruments that with some data logging, records that data to a format that can easily be replayed and verified against a lower-level component harness. So we've got kind of similar looking diagrams to what I showed at the start. We've got top-level system model highlighted in orange there, 3 components underneath that, and we've selected one in purple that we're pushing through our workflow. And the bottom screenshot there, which is new, shows that same purple component selected kind of on its own within the unit test harness there. So that's executing on its own using recorded data and will be verified against the recorded behavior from running in the system model. So we can do that with a whole bunch of different test cases, create a rather large run of regression tests. And then the beauty of this, if you actually just jump back one slide, is that can then be used every step of the workflow I just described. So from fixed point modeling through implementation models, personalization hardware tests, that same test harness, that same set of regression test data can be used all the way through. So that when we're running on hardware, we can have a really good confidence that we're going to match the model system behavior. So that was a pretty quick run through the workflow. I appreciate it. That's a bit of a light touch. I'll move on. Put forward another couple. Take you through some of that sort of middle stage, that implementation stage. There's a few design options. I've mostly spoken about Simulink so far. Simulink's normally the default option if you're looking at code generation from MathWorks tools, as far as I'm concerned anyway. It's what I recommend. It's a great visual environment. It's good for collaborating between different specialities, algorithm designers, implementation engineers, that sort of thing. You get a good helping hand in Simulink in terms of data types, so data type propagation, automatic growth control, that sort of thing. And you get access to some nice graphical tools like logic analyzer and things built to the model that most implementation engineers, FPGA engineers are familiar with. There's a lot of high-level function blocks shipped with it that's compatible with CodeGen, so you can drop in quite a lot of complex functions kind of free. And it's got the ability to generate active interfaces. There are a few drawbacks, which I've got on the slide, but I'm actually going to talk about them as I cover the next 2 options, because they kind of map onto why you maybe CodeGen different options. So if we flip to the next slide, the other obvious one is MATLAB code. So you can do VHDL without code generation straight from MATLAB. It's not something I really recommend in general. Primarily, not that much less verbose than VHDL, really. You've got to manage your pixel data types just as manually. You've got to control capacity, bit growth, saturation and wrapping, logic, that sort of thing. It's all controllable, but it's a lot more hidden from you. The only area that I can, in my experience, I can maybe give the option to explore is either if there's a very specific example or high-level feature that is compatible with CodeGen, which can straight from MathWorks implementation, or more normally, some certain bit flashing and logic operations. If you find yourself kind of in front of a similar diagram and you're thinking, oh, I know what I want to do, and I could do it in VHDL or Verilog very quickly. Chances are maybe it would be easier in MATLAB to draw that diagram. Recommendation would be to drop that into a piece of embedded MATLAB, which can then be wrapped up inside something or anyway, so you can make some increased functionality you need. So, if we click on the next slide, there's another newer option, which is an interesting one. There we go. Which are system objects. This is MATLAB's kind of class-based object-oriented type code option. Being a class-based mechanism, so a class can have data and methods that operate on that data. But with that, you kind of get the idea that that data has states. So an instantiate object has data which can have state, which maps really well onto hardware design. Kind of a little bit better than just a sequential MATLAB. Quite a lot of the high-level functions within MATLAB and Simulink already are actually based on system objects understood. So it is something that's relatively powerful to generate. And there are certain things in my experience that might be more easily expressed in code. So parameterized data routing or a kind of complex looping sort of implementation. So you've got something that you might write before generating from VHDL, for example. That can be more difficult to describe in a Simulink diagram, especially if you're trying to use things like the loop generator to customize what's happening inside that. So system objects are something we're exploring. They're a newer option, but they're used in code quite well. You've got the same drawback as MATLAB code, but you're writing to explain MATLAB code, which is slightly more time consuming or verbose. You click on the next slide for me. As an overview, recommend Simulink as primary mechanism for code generation tool set for almost everything listed there. I'll just highlight Stateflow as an option that less people I think have heard about. Stateflow is Simulink built-in state diagramming tool, which can generate some nice state machine state out there. VHDL very long. So for almost everything, Simulink got MATLAB code for you and system objects. We just jump on. Try and get done before the fire alarm goes off. Just a couple of areas to highlight where we're looking at developing the workflow at the moment. Primarily it's around looking at some in-house tools to expand on the capabilities of the code generation process. So looking at how we can add new extra features to the register map generation. There are some limitations in the tool. So if you're trying to do more complex register maps, you can start to trip up a little bit. And the same with the packaging, so packaging out for the Vado IP. If you're trying to wrap up some slightly more complex interfaces or non-standard interfaces, so you're moving away from just having axis streams that the tools kind of natively understand, we're looking at adding better support for that. And we're exploring UVM test bench generation as well, which is a newer feature of the HDL Verify tool from MathWorks. That's being assessed at the moment for use on projects where UVMs have our overall verification strategy. And just see how the monitoring side of things can combine that. And finally, if you click on another slide or two, perfect. Some advice on how you might pick up and kind of explore using these tools if it's something you've been interested in. I'll start with the real basics. If you never touch MATLAB and Simulink, get access to the tools, and then built in there are these on-ramp courses. That's the first thing. Kind of self-paced courses for covering the basics. If you've got access to paid training from MathWorks, that can be valuable. It's really good. But either way, start with something basic. Try and model some behavior or some functionality that you're quite familiar with. Experiment with the different options within Simulink. Try and move into Simulink over MATLAB pretty early. And then use the test features because they're going to be key to kind of creating a good workflow, I think, to get the hardware. So try out test harnesses, running in a test manager. Try out logging, recording data, and running against some baseline behavior. And then if we flip on to the next page, some HDL code specific things. First thing to highlight is lots of examples in the MathWorks documentation. In general, documentation is quite good for the whole tool set, but no different in the HDL code area. So look at the examples. Most things you want to maybe try you're just getting started, will be in there. And then use the wizards. I showed a screenshot earlier of the workflow wizard, which is how you run through basic code generation. That can get you down to the HDL or Verilog, and can get you through synthesis. You can even places where you generate a bit file if you're using a kind of standard dev board. But there's also compatibility wizard, which can help you take a simulate model and ensure or analyze it, see if it's compatible with the code generation tools to start with, and provide you hints if it's not, as to what you might change. User code generation report, I showed that report earlier, showing snippets of the VHDL that have been generated. That there's a lot of information in the code gen optimizations that are applied if you're doing automatic pipelining, or if you're doing resource sharing, or if you've got multiple clock rates in your design, that sort of thing. Those details are all in the code generation report, so get used to reading those. And again, start with a small model that you can understand the functionality of. It helps you kind of, look at the code and understand what's being generated. And then get into the test tools. So run the same test analysis, try and get through simulation. If you've got dev board, get running on some hardware. If you can do all of that, it will stand in good stead to be a real result. And that's me. I think if you flip to the next slide, there's a little summary of what I've been through, but I'll let you read that and take any questions if there are any before I run out.
Okay, thanks, Bill.
No worries.
Okay, I think if you want to switch it off and try and there is a slightly technical issue with the people online. That
Okay.
Then so the first slide, but don't worry.
Okay.
They heard
No
you.
worries.
Everyone in the room first, so we're just trying
Okay.
to get that. But are there any questions from the audience?
Yes.
How well do you think the MATLAB tools play people who are designers?
I would say support for Xilinx is probably better than some of the other vendors. I think support for Intel now, FPGAs is pretty good. The microassembly side of things is slightly less mature, maybe, but it is there.
And how does that
Say that again? Yeah. Could only be 20 seconds, so
Indicate the end of your talk.
it does, yeah. I was hoping to get done before it happens. Sorry.
it was very good and academics?
Oh yeah, I have a question. Yeah. There is, I did notice that MATLAB 2023A was released just very recently, and there is now support for generating the HDL Verilog with no vendor selected, so without a downstream vendor tool, which I haven't tried it. My guess is they're trying to get more vendor agnostic with the code generation. Before you have to have a vendor tool kind of installed and selected to get through a lot of the code generation process. That might be an option now, take you closer to some of those other vendors, but obviously you won't get the integration you get with doing automated hardware in the loop, or there's built-in features and tools like elaborating back onto a model synthesis results from Nevada, so you can see where your paths are in those. You actually obviously get those. However, some of those features I think are the less useful ones in the core code generation. So we're trying, if you've got a device you want to explore. The latest release.
It's a very expensive experiment.
It is. I think if you can get access to some trial by contacting them, then it might be something to explore. I think the latest release, they've also added support for it in the online version of MATLAB, which wasn't there before, and that might be a way to get access to it. I don't know if there's easier access to MATLAB online through trials. I don't know. We just have it. So,
One more question, then we'll move on.
Yeah, no, from Apple's systems, basically costs, processing parts,
Yeah.
often for sensors.
Yeah.
And in the US, we're seeing a lot more model-based system engineering sort of requirements flowing down from the government. They're sometimes requiring tools like requiring Cameo or Rhapsody and now I'll use those tools. How do those, how those tools play with MATLAB?
It's actually something that there's a team exploring at the moment on the site. it's very early days. I started conversations with them about that interaction, but that is an area of interest to see how we might flow from those sorts of tools and keep it tool agnostic, I think, into our existing model engineering workflows. And I think the MathWorks tool set for ours is quite a mature tool set. We want to kind of stick with that. So yeah, I'm not aware of many projects on site that have a requirement to use that tool set as a kind of like upfront component modeling type requirements capture, that sort of area. But there are some. I know there are some. So it's a topic to be with, which would be interesting.
I guess that tends to be, those tools tend to be sort of a higher level, as you said,
Yeah.
front end requirements capture
Yeah.
rather than that algorithm.
That's right. Yeah. At the moment, yeah, as I say, I think there are projects on site that use those tools. Others are still much more kind of like textual requirements using tools and things like that. Typically, at the moment, our modeling process starts slightly behind that, slightly after that stage. But I think it's an area we're looking at to improve.
Okay, thank you. And just one, we're out of time, unfortunately. Maybe you can ask if we do a break. Because we need to move on to the next speaker. We're about 5 minutes behind. But we'll give all speakers the same amount of time. And one thing I would just say, I've used the UVM generator, and it does work very well. So, okay, so thank you very much, Ben. Thank you. And Daniel? Hi, Daniel. Are we ready to go, Angela?
Yes.
Perfect. Okay, so our second speaker today is Daniel Ogilvie from, is it Singmai? Singmai Electronics. Okay, and his title is Teaching an Old Dog New Tricks, and we've got 15 minutes. Yeah, so we're still
I've got 5 minutes less than 15.
No, you still got the full 15. Still got the full 15.
Okay. Well, hello. As said, I'm Daniel Ogilvie. I'm Managing Director of Singmai Electronics. Yes, next slide, please. We manufacture intellectual property cores, principally for video processing, video transmission. Next slide, please. And we also make some real things, real hardware modules using our IP cores. Next slide, please. Once upon a time, a long way from here in the town called Malden in Essex, which is famous for its sea salt, I've become aware of a new device. Next slide, please. The PAL CE 22B10, an amazing programmable device that had 10 flip-flops in it, believe it or not. Next slide, please. Prior to the 22B10 arriving, we were all using TTL logic, of course. But once the PAL 22B10 arrived, various companies, say AMD and such like, started producing a range of these programmable devices. The 22B10 had 22 inputs and 10 programmable I/O input or output devices. Next slide, please. You have to be a little bit careful with the 22B10 because it was a one-time programmable device, so it was in the bin if you made a mistake. To program it, we used a language called PALASM, for those who are old like me and may remember that. And it was the first time that we started using text to describe the design rather than using schematic designs. And this is an example of the PALASM. I actually quite liked the text base, having been used to schematics up till that point. For example, you could just use find, control F to look for a port or something like that in the design rather than going through where does that module port link to. It also allowed comments on the code, which were a little bit more difficult for schematics, but the comments really weren't that useful. Truthful comments would be more like, this comment relates to the code as originally written. I had to modify the code to make it work, but I haven't bothered to modify the comment. or I had to add this bit of code to make it work. I've no idea why. Therefore, I'm not going to comment on it as I don't want to look stupid. Good luck trying to understand it. One other comment, the 22B10, 10 outputs. Now we have a 9 bit memory, multipliers, etc. in our FPGAs today. For video, we tend to use 10-bit wide buses. So you can't fully implement the devices. There's always leftover memory. It's just a comment for any FPGA manufacturers. Next slide, please. So we moved to Liz in Hampshire now. New company, very heavily into FPGAs. And the company didn't mind which devices you use. Next slide, please. The Xilinx software to me seemed to be a mishmash of different programs. There seemed to be DOS boxes linking up everywhere. You had to put in a little bit of text. Some was graphic, some was not. And a colleague also swore by Actel. But for me, Altera, they seem to have a good range of devices and their tools seem to be integrated. I think Altera actually wrote their own tools, whereas Xilinx and that farmed out, which is why nothing quite fitted together. Next slide, please. And another nice thing for us who are old, you got books. So if you wanted to learn how to use the code, you could have a book on the side of you and you could work through all the instructions instead of going through a 700-page PDF on your computer. Next slide, please. I was using Altera 10K Apex devices at the time and managed to get 95% utilization at 27 megahertz, so not so fast, but at the time this was quite impressive. Next slide, please. As you know, the Altera design software was called Max Plus, and the text language was AHDL, Altera Hardware Description Language. Step up from Halasm, but still pretty low level. Next slide, please. But that didn't stop us writing hundreds of pages of AHDL to implement the design. Next slide, please. We're now going to move to Waterloo in Canada, home of BlackBerry phones and Mennonites, a strange dichotomy. I was working with a company then designing analog video decoders, NTSC PAL. Next slide, please. FPGAs were still used to verify the ASIC designs, and this was now the company who were using Verilog. I was actually more an IC architect, but I had to read the Verilog, but I didn't actually write the code, I'd have to simulate it. Verilog to me seemed a logical extension of AHDL. Later in my career, I thought, I bought a couple of books on VHDL and proceeded to translate my Verilog design to VHDL. The experience scarred me for life. I slowly came to hate VHDL. VHDL seemed as though it was written by a prepubescent software engineer, Verilog by a mature hardware engineer, but each to their own. I wrote that comment before I found out that Leonardo were using VHDL, so whether I'll get out, I'm not absolutely sure. It was Marconi, I think, that started to employ art graduates for software design. They said they could think more abstractly. And that's why we need a 4 gigahertz processor to run a word processing package these days. Next slide, please. We now move to Samaburi in Thailand. It's about a 2-hour drive north of Bangkok. Home to curry puffs. They can be savory or they can be sweet. And also cowboy country, which some may not know or associate with Thailand. This is where I started Samurai, and as I said, we were selling video IP cores, and they were principally written in Verilog. Next slide, please. So we used FPGAs to implement the IP cores, of course Altera, and we were mostly using Cyclone 4 devices. Next slide, please. We then moved back to Ayr, not so far from here in Scotland, Burns country. Although, to be honest, there's hardly a place in Scotland that doesn't say it's Brown's country. I moved back here because I thought the business opportunities would be better than they were in Thailand. I moved back here as we left the EU, and then we had COVID. Again, demonstrating my acute business acumen and timing, and illustrating why I'm more to be found looking for spare coins down the back of the sofa than dining in 3-star Michelin restaurants. Next slide, please. And then this, one day. Due to temporary constrained supply, DigiKey is unable to accept back orders at this time. Next slide, please. Well, there must be other options. Mouser, Parnell, Arrow, different device. Nothing. Next slide, please. Okay. I keep getting emails every day. Apart from the ones questioning my virility and Russian brides, I do get emails from Chinese companies offering metal castings, PCB, and electronic components. So I ordered a couple of the FPGAs that we use from some Shenzhen company. It took 2 goes. The first lot didn't arrive at all. And then we got this device. It worked. We put it on the board, it's in the right size, and we managed to program it, and something came out of it. Just one thing. We had actually ordered a C8N device. If you look closely, this is an I8N device. That's a little bit strange because Altera have never made an I8N version of things. It just makes you wonder, you know, I mean, I could have something really valuable, like a misprinted penny black version of an FPGA, or it could be it's dodgy. Next slide, please. So I got some more quotations from different companies. The FPGA in question, I got about, it was about $60 pre-panic from DigiKey. Well, cute photo, Daisy, and you're very nice, but $667.80 for one FPGA just seems a little bit over the top, considering it's a pretty small device. Sorry, next slide, please. So I look, maybe we go back to our Xilinx or someone else. Nothing, absolutely nothing. Next slide, please. But what was this new FPGA company I read about in EDN or somewhere like that? Efinix? Never heard of them. Anyway, I looked them up, and I found the article, and I looked them up on DigiKey. Look, 39,000 in stock. $3.25, even the bigger ones, $5, $6. Oh, okay. They got my attention. Next slide, please. You have to buy a development board to get the software license. That's not a big deal. You don't have to buy an expensive board. I was only using smaller devices at Altera anyway, so I was using their free software. I managed to plug in the board, the demo board, flash the LED, I put the board in the bin, and now the real work starts is trying to get your own design running on their devices, on your own PCB. I had to use 2 devices. This is because I don't like to use FPGA packages, because we like to hand solder and hand inspect. So we used the largest device that we could use in a LPFP package or something like that, but still had to use 2 devices. That, of course, meant we had to split the design in some way, and it didn't really split in a good way, but anyway, we managed it. The board was designed, now we were going to switch it on. Next slide, please. The good thing was, we got no smoke. Power consumption seemed okay. I made a small test program, input clock to an output pin. Always good to start simple. I opened the design software. Oh dear, doesn't look like Quartus, does it? After 30 years of Quartus, I've got to learn what all these new things are at the top. But actually, it didn't take too bad. There's a couple of videos on their website that sort of get you started with something simple. Next slide, please. The only thing was, how do I assign the pins? There was no little graphical thing that Quarters has where you just put the pins across onto a package diagram. FPGAs have decided PLLs, tri-states, I/O assignments are not part of your Verilog code. A sort of wrapper thing that you've got to go and find, and you define it separately.
Well, they generally, they were originally designing FPGAs for inclusion in larger SoCs.
Right.
So that's why.
That's why it's separated out. Well, for a while, I quite liked it. But then I started to come across other issues. Their PLLs only have 3 outputs. That's a little bit awkward. We had to cascade PLLs, some jitter issues, etc. You can't reprogram the PLLs, which you can with the Altera devices. So that's a feature that we were using. So we have to find ways around, and yeah, just keep in mind that stock list and those part prices. Next slide, please.
You've got a couple of minutes left then.
Okay. So we've got a programmer device. You'll probably be aware that Altera sell this programmer for a very reasonable price of only £300. Of course, you can buy cheaper ones. We also found out early on that Altera sell their configuration E-squared proms marked as Altera devices at about 32 times the price of what the real device is if you just buy any CFI sort of compatible E-squared prom. Efinix don't offer a programmer. They tell you to buy this board, and then you've just got to wire it up into your own board. But they don't actually do a device. So we designed one, but didn't actually end up making it. We're still using that little TechNES thing, but it works, and we managed to program the device. Next slide, please. So we designed our proper module, and I haven't got much slide left, but this is their programming window. And here's the important thing: configuration done LED. We programmed to the E-squared prom. We don't tend to use JTAG. We're only using small devices, so we don't tend to bother with the JTAG port so much. So we programmed the E-squared prom. A little issue daisy chaining the two because we had to use 2 devices. But anticipating that, I put the link, so we just programmed one, got one programmed, and I got 2 pins wrong. My fault. If I'd read the 700-page document properly, I wouldn't have made the mistake. Next slide, please. About 3 minutes. Okay. One little issue. We've got this 1 pin across the 1 pin. Forget your RISC-Vs, forget your ARMs, forget your NEOSes. We have our own processor based on the old 6809. And in my days back in Morgan, this was our development tool, the Dragon 32 computer from Wales. Next slide, please. The trouble was, our own microprocessor, which we just use for bit twiddling and I2C control and reading buttons, displays, that sort of thing. Really simple stuff. Because we designed it ourselves and it was designed a long time ago, it was written in AHDL. Of course, we're using Altera, so we've never bothered to translate it. So one thing I had to do was change it to Verilog. And the other issue that we had was we had an assembler for this. Yes, an assembler, not a C compiler. And the code automatically generated what's called a MIF file, the Altera memory initialization file. So if you change your code, it automatically generates the MIF file. You just compiled the FPGA and it will automatically integrate your code. Because the processor is small, everything is using internal memory. Of course, that's not going to work now with Efinix because they don't recognize MIF files. So we not only have to change the HDL, but we have to go back to the source code of the assembler and that. We've decided to scrap that and we're going to find a different solution to it now. Next slide, please. We can go next slide. Yeah, we had some more problems. After we got the initial code working, we then threw the entire few 100,000 lines of code at the devices, and of course it didn't work. The devices we were using only have got 36 multipliers in. We need more than that. These are the hardware multipliers. But it's got a lot more logic in, and I thought the logic would take up the slack. It didn't. It burst the device. Initially, we just cut out the bits and pieces just to get something to file. And as I don't have much time left, I just say that we've managed to get it working. Next slide, please. So we're using FNX devices. Bye-bye Altera, and yeah, we've yet to come across the new issues which will arrive, which will be when we start doing the test benches and we find out that FNX don't support model sim as Quartus did. So we're going to have to get Icarus working and whatever, find some other solution. So it's this old dog's having to learn a lot of new tricks. But they're out there and the devices are working. So thanks for listening.
Okay, brilliant. Thank you. So we're going to move. So we have to move straight on to the Q&A. So our next speaker is Ian Pearson from Microchip. Ian, we're just going to. Just check one thing and then I'll let you go. Perfect. Right. From technical issues to solve. Right, our next speaker is Ian Pearson of Microchip. Over to you.
Breathe. It's always swinging if you break it 11 timetable. All right, let's next slide.
You've got an extra. We'll give you the full time.
Because you gave me extra time, so I've worked for that. I've got all these slides to get through. There's no way they're doing that. All right, so smart HLS. So this is talking about high-level synthesis, which is kind of the brief that Mike gave today. So I thought, well, we'll try this and give an intro to this tool and a little bit about it and try and give us some reasons why and why not, if you like. So next slide, please. Right, so why would you high-level synthesize? Well, ultimately, stop changing. And changing that on a schematic, yeah, got to redraw things, don't like. Doing it with some level of HDL, not a problem, it can be done if you've got the engineers and the time, and it fits in, and we can do that. Or we can go to alternate options, which is what we'll have a look at, which is can we use a different method with other examples. So ultimately, the idea behind the HDL tool is to allow you to iterate faster, develop a little bit faster, use different engineering skills because they might be available for that. But there's lots of pre-written algorithms which you can use a lot faster, which exist only in C++ and not in HDL. How do we get them to HDL and make use of them and test them and ensure that they're actually adequate for means and do that quickly without hand coding it, crucially. That's kind of the target. Now then, do you want to go? Caveats I'm going to put on this is that HDL is great when we go from C++ to HDL, but what's a lot of C++ is control loops and code and individual bits and if then bit. Doesn't translate well to hardware. Okay. So if we go, okay, let's look at this. Most of what we'll look at here with this environment we're looking at is where you're probably going to have some programmable element in there running some level of software behind it to do lot of testing with it is to come up with it, where they're giving some of those ideas of what you're going to gain, if you like, from a performance perspective, based on the fact that some of it is performance based on how much code I've got to write and maintain and understand to get this to work, and therefore how much I've got to maintain during that test and verification cycle. Less code often better. And I'm going to put a caveat in it. These little things swings around. I'm like, yeah. Now in C++, often you get a good C++ guy. He'll make the most complicated statement possible that nobody understands except him, and it comes up with some of those comments that were made before about comments in code, yeah, which I have no idea what it is, but it works. So let's go with it. And that's not going to be the best idea. Okay. So using an interface program with a web program is probably not the best plan. Somebody who understands hardware does, but we'll talk a bit more about that as we go through it. So bear that one in mind. Next slide. But to give an example is that Gaussian filter, fairly standard available in C++, 65 lines of code, relatively easy to understand, therefore very easy to maintain and test. In HCL, 276 lines of code without the submodules, which you've got to hand code, test, verify, and maintain. Okay, so there's a balance to look at there. So the intention there is that we're trying to some extent, go with something that's maintainable and fewer potential bugs in it. Everything's got a bug, okay, somewhere, just finding it. And therefore potential fewer, which is less to find out and less to have to go through the process of working out what's the code going to do and come back with a test load. And next slide, please. Output from it ultimately comes down to I need to make use of it, and just go forward 1 or 2. Hopefully, might build a farm one, please. Ultimately, you know, I'm trying to get my C++ code into some level of usable functional module that goes into the tool that gives me some level of output that says it works and how it's going to perform in a test engineering logic on the device to give it some level of performance characteristics for logic. And that's the intention behind it. How do I do all that flow relatively easy? Next slide. So the rough flow is that I'm going to create a new project of some form or import one if I've got it. I'm going to compile in software, which is basically using a GCC compiler. Okay, so I'm going to use it in a software environment here. I'm not opening an HDL hardware tool here. I'm going to do this in effectively this is in an Eclipse-based tool, so it's just opening a C++ environment. Okay, behind it is a lot of other things. I'm going to run that tool in that C++ environment because I'm testing C++ at this point. And I can run that, and it'll give me output, and it'll tell me whether I've got 1042, and it comes back with the right answer. Okay. I can add constraints into that. The tool will allow you to add a constraints file. So I can take the standard constraints, I can constrain the time, I can constrain all the factors that I wish to do for the hardware. So some of you are going, so there does need to be some level of hardware understanding. Well, yes, because I'm going to put this onto a hardware device. So we're not redundant. But there's less of us, which means we get an accelerated management position with lots of C++ people underneath it. It's just another promotion, isn't it? So that's still required. Ultimately goes into hardware, so that's going to give us some Verilog output. It's going to give us some typical scripts. It's going to give us a bunch of information to be able to put that into the hardware tool, crucially. Okay, and then I can actually then do cross-simulation to look between the C++ and hardware to make sure the two verify and test together, so I get the same output from both, crucially, and they compare. And ultimately, I can go away and synthesize that. Next slide, please. And one more. Missing a column. Right, cool. All right, so if we take from a perspective of, as I said, we're going to have some level of core in there, be it soft core, hard core, however we decide to put it in there. I'm going to have my C++. A couple of things it's going to generate for me that I'm going to need a driver. But I've got to tell the software, if I'm running it in the core, how to talk to the hardware I've just created. So it will generate that for you, thankfully. So I've got that software hardware overlap, and I can do that part of it. We can play around with how we partition it and optimize it. We'll talk a bit more about that one.
and then we get our output for our tool to go into the device. You get your software side of it to get your driver across, and then I can run my system software against my hardware, and it all just works magically. I've got a rabbit just here. Okay. It's all magic. Okay, that's the flow. Next slide, please. All right. We've been working on this for a while. So this is a company that we bought. I actually think we got them just before lockdown, if I remember rightly. I can't remember. I can't remember much actually, to be honest, about the last 3 to 5 years. So also it's been going through a series of iterations, and it's now got to the point where in 2022.3, here, which is the current release, everything's now integrated. Smart HLS comes within the Libero tool as a set of tool suite, if you like. But they did a lot of work in the background from where it first started, I'll say, on getting the quality and the predictability right to make your verification of it a lot easier, because you've got to trust what it does, ultimately, because you're asking a tool to do what you do by hand right now. And they've been looking at runtime improvements and quality improvements, and ultimately just basically making the tool better, and that's what they will continue to do. Device-wise, it only supports 4 of the family, okay, at this point, which is basically the more recent devices, what we call our Gen 4, Gen 5 devices, which are those 2 groups there. The older ones, no, it doesn't, and there's no intention to do so at the moment. So that's kind of where we tend to sit, which is where the majority of effort goes in anyway on the device. Next slide, please. Do 3 more. Makes it easy for people to read. Okay. So as I said, ultimately about slightly faster design cycles, ease of use. Looking at options, we're going to talk about this side in a little bit on area performance trade-offs. There are tools that show you what it's done, how it's scheduled, and so you can look at the design from what's it done in hardware and how it looks at the process you've given it in C++, and how does that verify through, how does it flow through pipelines in the architecture, those kind of things. It does have constraint handling, lots of fragments and things involved in scripting it in the background, and ultimately that gives us the integration into the main tool. All right, that's the fast highlight bit. Let's look at some deeper stuff. We want to go forward one, and then another one, please. Okay. And one more. Note to self, take the builds out of slides when you're not in control of the. You're sat there and you want to read it while I'm talking, and therefore having it all available. The big reveal of the marketing. All right, so similar process again. Ultimately, our goal is to get everything down here onto the device. Okay. Oh. Fish. That would good. Okay, right. No, don't touch the screen. It's a touch screen and it expands. And it might go for that. Yeah. Okay, let's try it. Okay, we're gonna push it up. We'll try a slide in the next screen. If it goes wrong, answer the you suggested it. All right, so that's the program. Ultimately, it's going to take generic C++, and we'll talk about what we can do with that generic C++ to hardwareize it. Obviously, within that, you can throw things in there which is C++, so you can put in things, OpenCV, that kind of thing towards it, and it will do its best job to create some from that. What we aren't planning to do is to put those domain-specific languages classed as in there, so we're not going to go beyond C++ with it, because it's probably taking them long enough to get to this stage. We will look at integrating, and it's in process at the moment, which is a thing called vector blocks, which we'll look at in a second, which is an AI level tool. But ultimately, the flow is kind of what's on here. Our job is to get from C++ into a combination of hardware design side to get through, to get our fabric, software design through to get into our building environment, soft console to get firmware written to get those all onto the device and bring the two together in the old way. We've just basically done an extra step in there to try and make things a little bit easier and make use of resources in terms of human and mental resources. Do we try it? Result we have to show. This way, find it doesn't do it on the web only here. All right. So a quick aside then, VectorBlocks is a tool that we have for AI and ML, in other words, matrix maths. Okay, for those the hardware. And so it's a set of IP blocks which is configurable to allow you to make neural nets of such like in a fabric. And it's a tool that which then is integrated in, so then you can write that, use vector blocks. Suddenly I've got that interested in that happening, don't have to do all the work. And again, a bunch of background tools to help you do the modeling. I bet it won't be built, will it? Because it's going to do something else. All right, so let's look at some caveats and a few things about doing a design. It primarily wants to use C++. Okay, some things will exist in C. Right, that's fine. Easiest thing, rename them as a C++ file. It will accept them. Okay, the reason being is that the tool and the effort has been put into the C++ side of it, so it will still understand C, because ultimately it's the same, just haven't got some of the features. And that's where you'll get the better output, if you like, if you take it to C++ rather than the C file. As we pointed out a little bit earlier, ultimately try and write code or have code which is more hardware oriented rather than web and fluffy pictures oriented, as it were. Okay. So it's got some level of logic flow in there. So a super optimized singular line of code that fixes world peace in C++ is great. But it'll go, because it doesn't really want to deal with it in hardware. It's not got that natural flow to it. You can look at C++ and you know it's got a natural flow, and you can see that it might synthesize, and somebody look at it and go, and there's somebody look at it and go, oh my God, how many languages it pulled in? Again, something to look at. So that's the first key point, is ensure that you've done that. And if you're not familiar with C++, it's not the biggest issue. Okay, you can write C, just call C++. Right. And it's not overly choice of how you follow it. As I said, we're not redundant, because what it won't know is things about explicit details of the hardware. Okay, it won't be able to do clock networks, clock domains in the part. It won't do triple module redundancy. It won't do all those fancy things that the hardware guys need to do to make things more robust. It's a conversion tool to look at the algorithm specifically. So there are bits where you're going to optimize it in. So some of those optimizations you'll still need to be looking at. Okay. And then, as we said, pre and post optimizing design is look at the C and go, okay, if we just make that modification there, that will make it more hardware oriented. Okay. And then there's bits I can do before and after, pre and post design. And like I said, what looks good in C++ may not work in hardware and may not look good when it comes out. Some things that you can do is that, a function call, for instance, can be optimized in a pipeline a lot easier if we set it up to be. Okay. And so we'll have a little look at what happens with that one. If you do it incorrectly, you can result in a piece of code which is very highly optimized and runs beautifully quick in the FPGA, but takes up most of the device. And that may be one of those unintended consequences of not looking at what it might do. So you can't just go, write C, throw in, done, job finished. Write C, apply common sense and logic. What I think it might do, synthesize and test it and go, okay, maybe if we just modify that and move that around, look at the difference. But because I can do it a lot faster, those iterative changes are quite quick, it makes life a bit simpler. Okay, I'm not doing that in our to do that, what we're doing, I'm going to rewrite the whole thing. Okay, but there is a guide. So it's not even in a PDF, this one. Sorry, this is all online. Okay.
No
And I'll
books.
say, and I'll say for why, because getting PDFs out of the marketing department and getting them all through process is a lot harder than doing direct to the web. So everything goes into the direct web. Well, most of it's up on GitHub. And so most of it goes to there nowadays, so that's why it's easier to do these things. So, and it also means they can update dynamically. So if there's fixes need to be done or additions, a lot faster to do with PDF. But I like PDFs, and I still find that difficult because I'm not old, but I did like books still. We read the day we start doing data sheets, but then we've all got used to it. And then I just the amount of them I threw away on a regular basis is huge. So, code simulation, obviously, it can do and is required because I want to know that what I've written in C++ works in C++. Because if it doesn't work there, there's no point in trying to convert it. It won't give you it will give you the same output and probably worse. How it kind of does that is that you've got your C++ code, you've got the bit you want to actually run as hardware, and then you've got main. Your main effectively becomes your C++ test bench. So that's the bit you're going to use to test the function you're going to optimize and pass across to the hardware tool. It'll also then create the test bench for the RTL side of it as well. So we'll forward that across the system to allow that test bench to occur in the hardware tool. So you kind of get both tools to then compare the output of both. And it will do that work for you and allow you to play around and optimize those. A couple of things on that still, though there are still a few caveats to consider. Again, nice big manual, okay, still available. And some examples to go and look at how these work and where they're based. It will fail if main doesn't return 0. And often people will return at the end of the main and not return 0. And then you think about it and go, well, actually, if I'm doing a test and I want it to fail, there are situations where, okay, I've not got the correct result, so I want it to return 1, and I want it to fail and say that the test doesn't work. So it won't then try and do the HDL conversion. So as you're going through that writing your test in C++, is to have those caveats in. But if I've got to the point where, yes, you know, I've made X equal 1 and it all works, I need to do my return 0. Otherwise, it won't build to choke at that point. If you incorrectly use pragmas, then effectively the code simulation won't start. So you have to be careful where the pragmas are there. You have to look at what the boundaries of the pragmas are in the manual to make sure you're using it correctly in line with what you're trying to achieve. Otherwise, it'll go and fail. And again, if you use incorrect array sizes, it will actually synthesize, but it will fail the test bench. As I said, it's a little bit of you can't do this hands-off brain-free. It does require a bit of understanding of what's going to happen when I've used the tool. Unfortunately, it can't yet do full cognitive AI and work out what you were thinking and come out with a result. But give it about a year or two, and ChatGPT might be before you know. We're coming. All right, a couple of examples then. Let's work it through that way. So these are all available. I'll note. So these are all training manuals that are up on the Smart HLS site on GitHub. So these are all. I've just pulled bits out of manuals so you can go back and reference everything, and it's all workable through the tool. So effectively, standard filter that's been created in C++. Keep an eye on that box because we're going to leave it for now and we're going to modify it in the next one. To make it work in hardware, I've added that program. And it's taken standard C++ and it will convert that and run it. Not optimized, it's just going to create something, which is what it will do. Okay. And that's quite happy. Okay. There you go. Okay. So the loop, however, we can do something with that to make it better. So we've got that option, of course. If we look at it from C++, everything is going to be sequential. I have to go through my loop, back round, through my loop, back round. As good as processes are, I'm actually going to run multiple parallel processes to do lots of threads, which is something else we'll do later. I have to look at how a processor operates and how code operates. I'm not going to benefit from anything. I can still run it that way, and it will create that code, which is what that piece in example 1 does. It's just going to run it sequentially and do it as though it's running in the processor, but it's going to do it in hardware. It's not particularly well optimized. But I'm going to run it in hardware, so why not have it so in pipeline? So I can actually make the hardware do more work, and it's actually going to load store run each time on every clock cycle. Therefore, I get a slightly faster output and get hardware optimization, which is what it's going to try and do. Okay. How do I achieve that? First thing you do is flatten out the loop. So you modify that two-step loop into a single step, and then tell it to pipeline it. And that's all I've got to do. It's nice and simple. Okay, what else could we do? So, back to the video side of it. Okay. Lots of filters to run. Nicely happily done in hardware. Best way to do them. Might pull them off a processor. Might be using it in line with it. Might run them, as in this case, actually run them as purely hardware. Okay, just with some level of setup. But how do I make that easier? So I'm going to look at this. There's going to run it in particular on that one particular example there. And how do I look at putting that block into a hardware module and make a streaming application this time rather than just feed it and let it run through as though it's in the loop. So actually just keep leaving this in a streaming hardware block. And it's not working. That's what looking for. No, right. So how do I look at then for making use of buffers? So if we take this simple example, 512 by 12 image, 8 bits per pixel, about 262K RAM, which we can put on. It's not horrendous. Okay, but it's still the power. I'm going to use all of my resources to do one aspect of this whole loop. So let's look at an optimal way. Equally, a bunch of time to actually fill the buffer. Then I've got to manipulate it in about. So I've got lots of latency I'm building in. So we'll go with putting buffers in. With our architecture, it works quite well because we've got lots of RAM in and lots of buffering, which is kind of nice. So how do I make use of that? Okay. No, I think it's not. No longer conductive. Quite normal. So in this case, effectively it's taken a 3x3 convolution filter, added 2 line buffers, and effectively just rotating around those buffers in the example. And that's effectively what it's going to do in this section of code with a few more modifications. That's a fairly simple change. No, was that me or you? I'm not sure. That was me. Power again. All right. Okay. Between the blocks, however, I've got to get the data between the two because now I'm streaming through. I'm going to run data through. So I'm going to put FIFOs in between effectively each of these blocks so they can pass data between them. And I need to put that into my code as well. So effectively, then it's going to make a few more modifications this time than it needs to allow for to make use of some underlying libraries. Okay, so the libraries effectively are look at them as hardware modules that we've pre-written to make better use of the architecture. Okay, so it's predefining FIFOs, for instance, and how to make use of them in the architecture, which means that the C++ guy can use it. It's got a hardware definition behind it, and you know what's going to happen. That makes sense. So and that's basically done by adding the relevant includes for the apps, telling it it's going to use those libraries. In this case, we're just going to tell it it's going to create some filters, which is part of that libraries. We're going to tell it this is the bit it's going to optimize, it's going to pipeline this section, and then effectively where the line buffer is. So it's done all of that hardware operation for us with multiple minor modifications to the original code. No, could you go to, I think? No, it's got a oh my god, whole mechanism. Still didn't check that one. All right. So all the things it can do then, it can look at doing multi-threading as well. So you can actually make use of another optimization to add threads into the code. So you can make use of that, and it will make hardware thread which is quite useful. No. Would you forward, please? All right, okay, so as I said, overall, make use of other resources and other skills, but engage brain, engage logic, and it's still a hardware function, so we can't, as I said, the whole point along this is don't just say completely generic C++, it might have to be modified slightly to be best suited. There's lots of accelerators that we've added into the library to help that, which you just need to be aware of, because obviously it's the same as using a library C++, you're going to make use of it. And all of those are implemented and available, and there are other things in there to actually make better use of active interfaces and such like the streaming across buses and other things. There's lots of extra implementation operations to look at. Again, please. Okay. Which is the hardware bit. Okay. It's best if the person writing C++ understands RTL and understands FPGAs, but they might not. As long as somebody in that loop can cast the eye over it and make a call on it, which is the whole point. Somebody can write the loop, test it, write the C++, run it through, know it's good, then you look at it from an optimization perspective. That helps. You might get a better output. It will output it, as I said. You could do nothing and just put top in there and it will make something, but it may not be great from a functional performance on the device or optimized area usage. So you're going to make a lot of iterative calls, but the point being they can be iterative calls and they can be quite quick because they're done in the tool rather than on the device. So I can test all of that up front. Not everything will make best use of the libraries, and again, that can be a call. It might be that you can do it better yourself in something that you've got predefined. So not all libraries won't necessarily always provide the route that you want to go, but they may. Okay, it depends how the code's written again. Right. And again, lots of examples of things to go out with how to try all these things out. And forward again, please. Okay. No, okay. Well, three, and one more later. Okay. So again, a couple of little examples of other areas where other libraries can be used and things that can be provided for different operations and mechanisms within the libraries. Okay, there's lots in there. It's a big tool, difficult to discuss in the time available. The limited playing I've done with it is fine, but you've got to get to a big design to make full use of some of it. My bread isn't that good yet. It takes a long time to do the FPGA design, I've discovered. Not the quickest process in the planet. Okay. Forward one, please. And one more. All right, so lots to go at. Fairly simple overview. There are lots of demos and more detailed information available on exactly how it works. Lots of examples, lots of work examples. They're all, as I said, in lots of different links and interfaces. They are all here. They may work in the PDF to get it. If not, the GitHub site where everything is held is the FPGA examples, which covers a whole bunch of things. So it does these examples here, which are sort of a tutorial we've looked at, and then some trainings which go through a whole series of canny filters and all those things. Again, streaming filters. It will do some basic stuff, even to the point of creating you a UDP hardware implementation, which is going to be kind of interesting. But ultimately, it's only throwing data around and streaming it, so it's fine. So now on the web, it's really available. And one more, please. Okay. As I said at the beginning, it comes in fairly familiar Eclipse-based IDE, provides some level of performance. Again, how you exactly want to use it, how you want to split hardware and software, that's your call. That's the bonus. It's down to where you put the pragma. One key point and one thing to remember is that as you're looking at your code, it will implement whatever's underneath that C++. So depending on where you put that pipelining function, everything that's included in that might be expanded into hardware, and you might not want that. So you've got to be sometimes careful where you place that pipelining function. Okay, so again, try it, you go, move it, try again, you go, all right. Or go, actually, I like the performance it gave me, and we'll soak that up because it achieves what we need to do, but I might go to a bigger device. So use that before. But they're all calls you can make now fairly quickly. That's the basics behind the tool. And one more. Thank you. There you go. Look at that, 11 o'clock, just after.
Perfect. Yeah. Well, thank you. Very good. I've got some questions on online, if that's all right. So we'll go to audience questions from here.
Everyone's just dumbfounded by the brilliance of it, you see. Or they want to pack it.
There's a question, yeah. The first question from the audience, I'll go to the online.
Yeah.
Is it part of the brain process, or is it?
Yeah. You know, it's one of those things that I ask when people ask me, is that live? I don't know, because I'm getting more free. I actually don't know. I think some of it is, to be honest. Yes, sometimes I don't know, I'll have to go check. Because I press go and it works, right? But I get the full license because I'm an internal presser. I need to set up a machine without the full license. I believe it is included now as part of the basic tool for when you install Libero. I can use it. But I will check.
I was interested in your like the use of FIFOs between the blocks. So in FIFOs have your full flags and empty flags, and if you've got a processor in an FPGA that's feeding into a FIFO, and that's faster than the next module could take, but obviously really in a full flag at some point, you want to be able to want to freeze the hardware pipeline, and so that will actually involve freezing every single register. So a clock enabled signal needs to be distributed in exactly the same way as a clock signal.
Yeah.
And FPGA architectures don't support this.
Yeah. Okay. So there is some in-depth on that one, how they implement it. If you're feeding it from the processor, it's basically the idea is to throw it at a block of memory and it will deal with it. Those the FIFOs are more for inter process where it's doing a series of filters going along. So, one is just feeding out to the next. So there's a chain moving along with that one. If you feed it from the processor, it generally you try and point it through a piece of memory through a bus rather than trying to do it through the process of feeding it directly. Because obviously it seems like not aligned with the intention. So once they've got a little bit of care and feeding of how you look at it, how you set it up.
There's another question.
Oh, sorry.
Sorry. It's a very interesting presentation. I've been a big fan of HLS for many years. Always I have a question for you. So,
Don't make it too complicated.
oh, it's going to be a good one.
Oh, I've got it.
So, microchip devices, we use a lot of them in the space and defense, which are very traditional types of services. How they go about doing it. How do you see the HLS tool sort of picked up and adopted there?
Well,
Because, to be honest, we battle with Libro daily. I've already spent some with Libro.
different group, completely different group, so it's fine. Yeah, honestly, yeah. The Libro guys are in one part of the world, and the HLS guys are in Canada. I was pondering this actually, thinking it's part of our core market, and this is actually part of the spreading out into other areas, and some of that is any given market area have their requirements for adoption and how they do things and how they go at it. Okay, so we had a model-based simulation this morning. There's an acceptance that we're going to take code that's been auto-generated by a model, which we check. Okay. There's whether it's new, if you like, taking that C++ approach. It's a new approach in some respects. It's kind of not, let's face it. We talked about years ago. It just never worked. Yeah. I mean, I remember years ago, but it just didn't work very well. And so this seems to be actually providing useful output now and doing things relatively well in how they've gone at it and how the guys have written this over in Canada. And so it's going to create some output which actually is not going to remain constant if you modify it each time. It's going to be like a compiler, isn't it, ultimately? There's a potential every time I press go on a compiler, but it doesn't create the same code each time. Always the potential. Okay, and then you accept that, as long as the output's correct, and you've bounded it and you've tested it, and sometimes you freeze it. So I'm going to put it on the, I don't know, but there's going to be an acceptance criteria that a given industry is going to say, we're going to test this, and we like what it does, it gives us efficiency improvement, but we need to know that it does this, and we can freeze it and make it do X. And it will always repeat that section of output, or we know there's predictability in it, which is kind of what they're trying to work to, is to ensure that what comes out of it now is predictable, reliable output that you can go and do a standard verification test on and go, I'm happy that the two do it. Okay. But it's going to be down to the people who are accepting it at some point. That's my read of it. Yeah.
Okay, so one question online is quite a long question. I'll try and cut it down a bit.
Okay.
It's about, you know, software engineers, how much understanding of the FPGA do you think they would need, especially on those, you know, the unrolling of loops and that type of thing?
Yeah, another one was ponder on the plane yesterday. If you go, all right, if you took a, and I've been trying to put that through in some of the points through the presentation, is that I've joked about this since I left uni with one of my very good friends who's a very, very good C++ programmer at the time. And you go, yeah, look at this, I can make this line of code do this. And I'm going, yeah, but it doesn't mean anything to anybody except you. So how do I maintain it? But if you've got a guy who is a firmware level guy, okay, rather than a web guy, the web guy is going to go, what's a processor? The firmware guy is going to go, I get it, I have an understanding of it, and it's easier to teach them, I would argue, to make simpler code which is sympathetic to what you're trying to do from a hardware perspective.
Yeah.
Don't do overly complicated things that are very neat in C++ world, but they're only neat in the C++ world.
Okay.
So it's that bit where you're doing the loop and rolls and you're doing those. Yeah, don't make it that it's ego programming, we used to call it. It makes you look good, but because you're trying to keep your job, and because only you could ever modify it, right? It's that training. I think it's going to be to train the C++ guy to write more hardware sympathetic code than it's to make them write RTL. Yeah. And it's that balance in the two, is that you're trying to gain efficiencies in the process. So.
Okay, two short questions now. So, which SoC-based development board would you recommend to start?
Well, obviously PolarFire, because it's the latest and it's better. And it has to come from Microchip, crucially. I would go with PolarFire SoC. You don't need the SoC board unless you want that level of performance in the processor cores in hard cores, because you can run it with a soft core. And lots of these run on just PolarFire in soft core. So.
Okay. VHDL support? You mentioned with that, didn't you?
Yeah, it's not. It's very long. It goes to so.
It's just very long.
Yeah.
Okay.
That's the point raised earlier about VHDL being raised by some devil child. As it were. Yeah. At the moment, it's very long. Yeah. I don't think there's any no support.
Well, because you mentioned at the beginning there's more software engineers and FPGA and there's possibly now more Python engineers and
yeah.
engineers. Is there any plans for Python?
We've just got C++,
Okay.
and it's trusted. What was the metric I saw the other day? It's going the speed at which different code runs, and Python is almost guaranteed the slowest code to run on a machine by a significant factor.
Yeah, but so, that's why they
and people throw it out there because it's very library based. But the point there is security hat on, okay, and other things. You don't know what you're pulling in, and you don't know where it's come from. You don't know what the content is, and it's very, very heavily library dependent. And Python is about efficiency in making certain things, and it's going to pull in libraries from God knows where that you have no idea what's in there, and you've got to put that into hardware and trust it. Yeah, sorry.
The target is bound.
And it's okay. So C++ is some of that, but at least you have an idea what's in it, and you're more in control of that. I think is the key point. So, I mean, I've seen a Python one, but I think you end up writing very basic Python, very simple stuff without libraries. So.
Right. Okay, brilliant. Thank you very much. I think we're into a break now. So.
I don't think so. I will ask the question of the guys, but at the moment I don't think so. I think they want to concentrate on getting that one working quicker right now. But I can imagine if it's that point of if to go to the defence and aerospace level, if they want VHDL because it's DoD requirement, then it might become a DoD requirement if we do it. If they go, actually we like the idea, but it needs to be VHDL. It's not the end of the earth. They're both structured languages in some respects, so it's down to you might go with it because that's where the guy came from with it. In reality, if you look at it, it's not massively similar. But at the moment, I don't know is the answer. I can't have the marketing whims of what comes next.
Okay, so we will give it a proper clap this time. And we'll break in. Break to 11:30. Everything's in the room, isn't it? Really. Yeah. Yeah. Yeah, I'll take you up on that.
Form the queue at the door.
Thank you very much for your interest there. Yeah, I've been watching. I'm more ASIC.
Yeah. Right, well, I remember. Yeah, because I remember silent discussion 10 or 15 years ago was like, hallelujah about it coming out. And then it went, yeah, and then it's kind of kept up. Well, at some point, you know, you wouldn't try to put your, go to one. Yeah. Well,
I know Sammy True. It's just a different. Everyone yeah, I thought that. It just wasn't the way my brain worked.
No, thank you very much, Len. Thank you.
Yeah,
I know, I'm not many things that you're right.
Everyone's going to high level design.
Right,
Right,
we came up here.
I'm not mute now. You should be able to hear me. Okay, the technology is working. We do have to stay on time though, because people online will join at the right time. Okay. So our next speaker is Noah Donaldson from Annapolis Microsystems, based in the States. Noah is Chief Technical Officer of Annapolis Microsystems and has worked there for over 20 years in several engaged engineering capacities and in business development. Noah has most recently guided the technical direction and product development of the Annapolis' industry-leading 100 gigabit ecosystem
That's right.
that is aligned with the SOSA standard. He holds a physics BS from Carnegie Mellon University. Thanks, sir.
Thank you. Thank you all. Nice to see you. What's the swipe left?
Very detrimental.
Yeah, so probably speaking about, probably speaking a little bit more about hardware rather than software firmware per se. One thing I'd like to, that I'll be speaking about is MOSIS, so that's modular open system architecture, and I'll be speaking about that from a kind of a hardware perspective. Probably you all are sure familiar with open system architectures like VME, VPX, things like that, and some of those advantages. What you might be less familiar with is what's happening in the U.S. over the past few years in terms of aerospace and defense, and kind of the movement that's going on there. So just a sort of a brief history. The things you probably are almost certainly are familiar with are, VITA being one of the main standards bodies that deals with open system architectures, and VME, VPX, and then Open VPX being some of the standard architectures that are used for sensor level system development. Something new that's come on in the past few years and that we at Annapolis Micro have been very involved with is SOSA. So this is sensor open system architecture. So it's basically, it's leveraging Open VPX technology and standards, but applying them to specifically sensor systems. So they tend to be high bandwidth systems and systems that require a lot of processing. Next slide, please. So in the U.S., open system architectures, especially SOSA specifically, is really being driven quite strongly by the DoD. So we're starting to see requirements in large programs for systems that that must be designed to meet SOSA architectural features, and must be designed to be compliant with SOSA, or at least there's a very strong desirement that they be compliant. And kind of speak through, these are, VITA you're familiar with probably. SOSA I just explained. CMOS essentially is very similar to SOSA, but was developed by the Army kind of a little before SOSA. So these have really, they're almost exactly the same, but SOSA is across Army, Navy, and Air Force in the U.S. And we're starting to see some adoption by European countries as well, because there's just such a strong industry base in the U.S. that it makes a lot of sense, to get products that are SOSA aligned as well. Next slide. Did you have a question? No. Okay. So some of the kind of benefits that the government is stating are some of the sort of the obvious ones for open system architectures. I won't go through these in great detail, but it's enhancing competition, it's improving technology refresh, so it's allowing systems to get upgraded much faster. So you can take out processing modules and put in next generation processing modules into your sensor systems, because these modules are now intercompatible and have the same pinout, the same interfaces. So that becomes possible. And then, some of the big advantages on the industry side are ability to innovate and spend less money on R&D, just on designing sort of custom design modules for different customers. Instead, we can innovate on, the actual, what the processing and things like that are happening within the module, but not worrying about changing interfaces for different prime customers. Next slide. So getting down to a little more of the details of SOSA, SOSA's basically taken open VPX profiles that already exist, and it's gathered together industry and government partners. So you have industry members that create components, semiconductors, processors, connectors, microchip, and others, as well as industry partners like ourselves who do board level products. Also, integrators and those like Leonard who are doing applications and system level integration on platforms. And then also critically government and users who know what sorts of features and needs they have for now and in the future, and they can kind of communicate those future needs down through the chain and make sure that SOSA applies those features in everything that's done. So OpenVPX had a lot of user pins, and that basically meant custom pins. So modules that go into OpenVPX systems often have a few pins that are custom. That means that a lot of these standardized VPX systems actually have custom plug-in cards and custom backplanes. So SOSA defines all of those pins. So they take into account all the end user's features and requirements, like security features, low latency control features, things like that. They define these are the features we're going to need. Therefore, we need certain pins assigned for these things, and that way they're able to truly standardize the hardware profiles that are being applied. SOSA also reduces the number of VPX profiles. So there are dozens, maybe hundreds of different open VPX profiles for plug-in cards, which makes every VPX system really different from every other VPX system. SOSA has reduced that to just a few different profiles. So you actually can have a standardized system. You can upgrade modules. All of this is leading to a lot more innovation and again, ability to use more R&D dollars on actual innovation. Next slide. So a few of those innovations that it allows are generally higher bandwidth, higher channel density. It allows us to integrate some of the key hardware interfaces that we need. So we need high bandwidth copper interconnect. We need high channel density in terms of coax RF connections, and we need high channel density in terms of optical I/O for some systems for fiber optic. Next slide, please. So getting down to that's kind of a high-level overview of SOSA and what we're seeing in terms of a movement in the U.S. SOSA and what it's driving. Getting down to a little bit more of the details of what industry is coming out with. Some of the three kind of challenges that we're seeing in any kind of sensor system, whether it be airborne or in whatever environment, process the electromagnetic spectrum faster and with a reduced size, weight, and power. More agile digitizing and processing, because you never know what types of systems you might come up against. It's harder to know what they'll do and what frequency bands they'll operate on. And then also increased heterogeneous processing. So that means most of these sensor systems that can control have an FPGA at the front, but they may have a range of different processors on the back end. They may have FPGAs, they may have GPUs, they may have AMD or x86 processors, other things. So those are kind of a few of the challenges that I wanted to walk through, some of the solutions that are being worked in industry based on the open system architectures. Next slide. So first, looking at that first challenge, which is processing the electromagnetic spectrum and doing it in smaller form factors. We'll address that here. Go to the next slide. So a few of those form factors that are being applied, VIA74 and 90, which is VNX form factor, and also 3U short. So these are both part of SOSA. VNX is a form factor. It has a backplane and a chassis and pluggable modules, just like OpenVPX, but it's quite a bit smaller. So it's about 80 millimeters by 80 millimeters for each plug-in card. So it's maybe a third the size of 3U OpenVPX. So you can do things in backpack size things or smaller pods on aircraft, things like that. The 3U short is a little bit bigger than that. It's a shorter version of 3U VPX. And then we're also seeing some sort of standalone and more unique form factors and looking at how those can be applied to some of these in sort of a modular way to all of the rest of the standardized form factors. Next slide, please. So this product will be coming out later this year. It's both a digitizer and a processor. So it has very high speed A to D and D to A conversion, 64 gigasample, as well as FPGA processing integrated into one product. And it's a very small form factor. So it's about half the size of a credit card. It's 35 millimeters by 85. So this can get integrated. Either you can put one or many of them behind a sensor, or you can put them on VNX cards or on VPX cards. Put a few of them on VPX cards. So this is kind of giving that ability to digitize at a very high bandwidth as well as process, and then apply that to many different open system architectures. And you'll kind of see a trend of how this similar technology is being taken to the other open system architectures as well. Next slide, please. Another product is an FMC-based product. So SOSA doesn't define how one implements anything that's on a plug-in module. They only define the exterior of the plug-in module, so the pin-out to the back plane, the front panel interface, the physical form factor of that module. But one common sort of design element is the FMC card, so an FPGA mezzanine card. So this is one that's using Xilinx RxSoC Gen 3 based processor. And then this can be plugged onto SOSA aligned OpenVPX 3U modules, 6U modules. Next slide. So looking at kind of the second challenge was addressing more agile adversary systems, so systems that are working at frequency bands that we don't know what they will be or they might change. So to address that, we're looking at more of this direct RF digitization. So that means utilizing the very high bandwidth converters that we showed a couple of slides ago in
in more places. So if you, are sampling at that high rate, 64 gigasample, then you can digitize a very wide bandwidth, 20 gigahertz or more, and therefore you can have very simple and open front-end analog architecture that's able to look at a very wide band. And instead, in the digital realm, with software, you can control, what bands you're going to be looking at. You can go to the next slide. So for that, this is a product that we have out already. It's doing the 64 gigasample per second conversion with 2 ADC channels and 2 DAC channels. But it's doing that on an FMC card so that you can integrate it with SOSA-aligned FPGA boards. And it has a bunch of integrated sort of hard cores. These are probably hard to see, but there are digital down converters, digital up converters, so that all of that's built in so that you can digitize that very wide bandwidth, 20 gigahertz or more, but then you can sort of zoom in, so to speak, on the bands that you're interested in, and you can tune around on those bands. So if you only need a 4 gig bandwidth, but you need it, from 16 to 20, you can, look at that, or you can go down to lower bands, 0 to 4 gig, et cetera. Tune anywhere in that range. Next slide. Thank you. Sort of continuing to apply, the direct RF digitization, but increasing the channel density on the system. So we're getting to a system where we have 4 channels of ADC and DAC, and we can combine the digitization with the processing of the FPGAs in a 3U card. And then this also has the ability to plug in what we call an analog interface mezzanine card. So you can plug in different kinds of analog filtering or tuning if necessary on top of this card and still fit within the 3U DPX space. And then the third challenge is heterogeneous processing. So the big thing to address there is it's not just doing sort of FPGA front-end processing, but also how do we get many gigabytes of bandwidth around in a system using ruggedized components so that they can exist in an aircraft or something like that. Next slide. So a few of the processors that are being used the most in these types of systems are FPGA processors like from AMD's Xilinx and Intel. And the next generation of those are having some other advantages, like more GPU-like vector-based processing, as they call them, AI engines, and this direct RF conversion that I addressed, but also more and more GPU processing for machine learning and things like that. Next slide, please. One of the products that will be coming out soon is this one based on the Xilinx Versal. So the Versal is the newest generation of FPGAs. It'll have this pretty large size of FPGAs on it, as well as 300 gigabit optical transceivers, and also a mezzanine card. So if there's more RF that you wanted to digitize, like put that 64 gigasample per second converter on here, you could do that. Or you could have more optical I/O if your system needs even more optics, more optical fiber I/O than that. And then in terms of addressing the bandwidth problem, so if you're going to digitize all this data, very high bandwidth, you're going to have tens of gigabytes per second that you need to send around the system, module to module. So how are you going to get the data there and process it? There's within VITA, a new standard was started, VITA 91, It is basically, it has looked at a higher density VPX connector. So for the past 10 years, the VPX connector has been generally from TE, this multi-gig connector. It uses wafers. It has a certain pin density that's a bit limited based on its technology and a certain speed that's a bit limited. With this new connector, we can double the number of pins and double the speed. So it'll run at 56 gigabaud per pin or per lane, per transmission lane, instead of only 28. And then next year it'll double again to 112 gigabaud. So we're getting much higher density with this connector. So this is being applied to switch profiles. Because in 3U VPX, the switch profile was really the bandwidth limiting factor of those types of systems. If we go to the next slide, show one of the first chassis that's being released is this one. So that's a 13 slot backplane. So it has 8 payload slots, which are these first 4 and these next 4. So that's where you put your processing cards, 2 power supplies, clock slot here. All those slots are standard OpenVPX SysOnline. The 2 blue ones are the new slots that use this new connector. So those are the switch slots. One connects up the data plane and control plane. So that would always be Ethernet. Ethernet is the only protocol that's allowed on those. There's a new switch coming out that will be able to, just in one slot, they'll be able to connect up all 8 payload slots. Previously, using standard VPX connectors, you needed 2 separate slots in order to connect 8 payload slots. So you reduce the system size by 1 slot. And then our other slot, slot 6, it connects up the expansion plane. So you can either plug an Ethernet into that slot and have 100 gig Ethernet connectivity, or you can plug in a PCIe LVDS switch into that slot. So if you have GPUs, x86s, you can connect up using PCI Express to those slots, or you can use LVDS. So some systems, especially jamming types of systems or radar systems, you may need some low latency control signals in order to handle blanking. And so an LVDS switch can be plugged in here to handle low latency control over that expansion plane. Go to the next slide. So this is showing the Ethernet switch that can plug into an Ethernet slot. So it actually has 2 separate chips, one for the data plane, one for the control plane, so that you have separation between those planes for those who want that. And there are 2 FPGAs, Zinc FPGAs, as processors to control those switches. You could also maybe put some encryption in those or things like that if you want connectivity between. Next slide has, so this is the PCIe LVDS switch. So it has, this is showing the connectivity to the backplane. Each of these blue boxes would go to a different payload slot. So the green lines are PCIe going through a couple PCIe switches. So you can basically, with software, you can control for each card that's plugged into a payload slot, is it going to be a PCIe card, or is it a card that uses some LVDS for low latency control? Then you can set that up in software, and all these LVDS signals, the red ones, are sent to the Zinc. So then you can program a switch into that Zinc, either a hard-coded switch or a augmented switch if you needed that. A lot of options. So summary, there were these 3 different challenges that we've seen. A lot of our customers come to us with. We've kind of addressed them in those 3 different ways using open system architectures, and are far more challenges, frankly, than we would have been able to address had we not had that open system architecture sort of framework built on. Thank you.
Okay. Any questions in the audience?
Probably VNX.
Just because it's that level of size.
Mm-hmm. Yeah. Yeah, I think, it's more useful in space applications with CubeSats, so it's getting a lot of interest there. Thank you.
Okay, thank you. Hello. Final speaker. It's Patrick. Okay. So Patrick works at Reflex CES, correct?
Yeah.
Yeah. He's nearly 15 years of experience in the FPGA market and a hardware engineer background. He provides sales and technical support to his customers in various high-end applications and markets. And the title of the talk is an overview of JESD 204B and C implementation in FPGA SOM. Thank you.
Yeah, thank you. So I will go easy for the last session, or it'll be a light one. I will provide some introduction about what we are doing for JSD 204B, what are JSD 204B and C, and what we did to help our customers to make the step and help them to develop their solution. Okay, so why JSD 204? So the market requirement, so I don't know if you are all aware about what is JSD 204, but the market requirement was to have something that is efficient, that is low power, low pin count for the analog converters. For embedded especially, you need to have something that is low power, small, and also where we can go to have a higher resolution, higher speed, and have a better and higher frequency range for the JSD204. So from the LVDS part, so usually it was CMOS, then LVDS, and then we went to the JSD204, which is really reducing all the number of lanes to have a better and more efficient solution in a smaller package. So you can see here the maximum lane weight on the LVDS was up to 1 gigabit per second. We have more analog converter now going higher than that. But the JSD is really setting a new paradigm for having something that is more efficient, more powerful in terms of frequency, that also open more application in terms of frequency and analog converter in the smaller package, as I always say. Next slide, please. Okay, so what are the advantages of the JSD204? By reducing the number of lanes, so as you can see here, that was for DDS. So if you want to go from higher bandwidth from a converter, you need to increase the number of pairs. So you will have really, I think for hardware engineer, you will struggle to route every pair on the PCB. You will have bigger packages also for analog converter. So that's where JSD has a really big differentiator, is that you can go from that number of pairs to only a smaller number of high-speed transceiver lane, and you can have a better bit rate, better bandwidth in a smaller package. So by having the transceiver on the JSD analog converter, you can reduce the package. You can reduce also the package size by having a smaller pinout. Also using the CMA standard for the transceiver, you are having less power, so a low power solution. And the only drawdown that you can see going from NVDS to DSD was the latency. You have some application, for example, like countermeasure application, where the latency is really critical. So on NVDS, that's easier because you have the parallel data, you have the clock, so everything is with the clock on the bus, so it's easy to determine latency. For the GSD, the good thing is that you can encode, you can do the clock recovery on the data, and you can also have a deterministic latency. I will go a little bit deeper on how we can achieve that deterministic latency. In terms also of layout for our CAD team and hardware designer, is that you only have to route the transceiver, the sync clock and the device clocking screen to the devices between the FPGA and the analog converter. So that's simpler. That's smaller package. That's more efficient in terms of power, and also that you can achieve really high bandwidth, as you can see with that DSD240 up to 12.5 gig, and for the 204C up to 32 gig. So this is a simple, not up-to-date, it's an example. So for CV radar, so simple radar, so you can have your analog front end here. You have your ADC, your analog converter, indeed at 250 megabits per second. You need only to have to route the transceiver to the clocks here, the clock and the control command, and you can multi-device analog converter on the front end. All of that into an embedded system with a custom carrier board here. So you can develop your own analog front end, route that to the custom carrier board, and then going to the system on module based on FPGA, where you can fit everything to the GSD IP based on the transceiver of the FPGA, and using the power of your FPGA module with the system on module, so the processor inside, the memories, and you can do all the processing into a single solution. So that's one example. You can, if you're familiar with the roadmap from TI, Analog, or other manufacturer of analog converter, but that's clearly the trend, is to have higher bandwidth, higher frequency range that you can achieve by that. And yeah, that's typically where DSD 204B and C shine, is having something that is really low power, high bandwidth, high performance in a smaller footprint. But because there is always a but. So the challenges from going from the LVDS-based analog converter to the GSD204, that you will have some challenge. The challenge, what are they? The FPGA coding is a little bit more complex, because going to the GSD204, you have the application layer, link layer, transport layer, data layer, so you have more layers to go through. And what means going through more layers in terms of development compared to FPGAs, that in terms of debugging, in terms of troubleshooting, that will be more complex. And so that you are just moving the complexity from the FPGAs, where it was more focused on the hardware side of the routine. You are more moving that problem from the FPGA development applications. And also going from higher speed, having transceiver up to 32 gigabits per second, that comes from hardware challenges, more on the routing, choosing the right material for the PCB, the right stacker, having also the right high-end FPGA in front of that. And for that FPGA, you will have the power tree, the clocking string also to take care of. So it's really moving the problem elsewhere. That's really the challenge. And just to slay the challenges, it's going from a fully functional golden, what we call a golden design, golden platform. So it's using some FLC from the market, some prototype from the market. We can prototype earlier your design and really go from the proof of concept, your early design, to the final implementation in your final system. Okay. We talked a little bit about hardware now. So what we are providing for our customers to move from FPGAs and to try to onboard them into the GSD204B and try their first design sample. And also for those customers who are already familiar with GSD, using our system on module from Reflex and a small evaluation board also coming with that module. With an FMC, so the DAQ2 from the market, from another device, you can set up easily a golden platform, golden reference design to start a proof of concept. So we're going to modify our basis architecture, but basically you will have to do this demonstration. So we put the FMC on top of the module. We can connect an oscilloscope, a signal generator, do a simple loopback here. So we will have to acquire the signal, but loopback, and you can display the result from the AC on the oscilloscope, and also you can use the framework from another device to put that into their software application. That's basically the high-level overview of the reference design. Just to start in a minute about using and start prototyping some analog converter application. A little bit about the DAQ2 FMC board. So that's based on product converter, so 180 on the right. So based on the AB 9680 and 9144. We have the clock scheme here. And this is the FMC, the HPC FMC connector connecting to our system and module. We have the 4 transceiver for it. You have all the system clock, all the clocking string that will be used to set up the clocking of the FMC, the clocking for the analog converter. And that's really easy to use with the analog device framework. I will go to more details just on the next slide. I will just present the quickly the module. So this is our system on module, so what we call Achilles. That's based on Intel Area 10 SoC module. So this module is really dedicated for embedded market. So it comes with a small size, so 3 by 95 millimeters. What we did is we have both FMC connector on bottom and on top. So it allows you to use directly some FMC board from the market on top of the module. And the good thing is, with that module, it can be used with up to 2020 IO for NVDS analog converter. But also with the 24 transceiver, you can use this module also to move to GSD204. Right. So this is the architecture of the DAQ2 board. So as I said, you have here the PLL for setting up all the frequency that will be connected to the 200 converters. You have the 4 lanes up to 10 gig for the GSD204B. That the standard GSD204B can go up to 12.5 gigabits per second. So for this board, it's 10 gig. That's limited. The 10 gig are limited by the FMC standard, the FMC connector, which is the transceiver are up to 10 gig. So for this one, so as you see, you have all the connection here. So you have the clock coming into the design for synchronization. You can set here the clock and the 6-watt clock for the panel converter. And yeah, that's basically as simple as it is to start your first design and start getting up to the GSD 204. Slide, please. Okay, so a little bit more detail of the reference design. So what we use the standard framework from Analog Devices. So on Analog Devices website, you have a flavor of different reference design for each of their evaluation board. So we chose this one because that's simple to set up. That's also simple to get up to speed with that design. And they are providing full reference design for the software for the different breaks of the GSD2 data layer. So the application layer, as I said, transport layer, link layer, data layer. All IP are provided on the device. Also the software running into the processor inside the system of module. So what we need to do here is just take the preference design that sometimes we provide for an evaluation kit from dividing some Intel, for example, modify that and just port that to our system on module. So just some rough number for the setup. So setup, we run the demo at 5 gigabit per second. This is the limitation by using the top connector on our module, as we have both connectors connected to each other. When you are using the FNC on top, you have a stub, so you are limited at 5 gig on top. And that's why for this demo, we are just running at 5 gigabit per second. Just, for example, the customer can use that design at 5 gig, and he can, for example, do his own carrier board for the module and just modify the device tree, the clocking string to go up to 10 gig by using the bottom connector of the module. I'll explain a little bit details about that in the slide. So here you have the system on module, so the HPS, the processor side, running. So you will have a connection to a computer to run the analog software, the I/O oscilloscope. That's also handling all the data paths here with the memory interconnect. So that's actually the bridge between the FPGA side and the processor side. And here you have all the data path that you can have if you know the link transport layer and data layer. So this channel here is handling all the data paths coming from the DMA and just handling all the GSD IP, transceiver IP, which is basically using the transceiver of the area 10, but with the on top all the data layer for the GSD2. That's the same for the acquisition. So you have here the transceiver IP for GSD2, the data layer, and you can go up to the 54 DMA up to the application layer. So that's the setup of that demo. And in terms of resources, as you can see, that's really pure logic resources used. So as a reminder, the FPGA, the IFN used for this demo is a 660K logic element. So we are only using few logic elements just for that demo. And you can see that's that's quite complex in terms of IPU and code and resources utilization. We are using 800. And for the just in terms of power, for the complete setup, you can see the module and the carrier board, that's 28 watts. But just an estimation for the FPGA is only 8 watts. So that's really showing that for embedded application, the GSD to 4B and the analog converter plus an FPGA, that's something that is really low power and can achieve really high performance. So that's quite big for this demo, but you can go higher, of course. And yeah, that's just showing the power of using GSD with an FPGA in embedded application. Thank you. So this is just showing the data path from a high-level overview. So here, so you will have the I/O oscilloscope. So that's basically the software provided by Analog to analyze the different data sample. You can do there some FSP analysis, etc. So that's the I/O oscilloscope that is just configuring here. You can set up what you want to acquire and visualize. And that will also set up the data that we are looking back here. So going from the HPS, so the processor side of the IATN module. So you have the configuration. So that's where the Linux OS that is running on Achilles on the HPS side. So we have the IATN, use the driver, we configure the VDS, and that's where we send the data to the DAC, do the loopback, and for the acquisition, that's there is some the lower path. You will have the acquisition here, so handling all the EID204B data. From packaging the data, send it to that DMA. The DMA will store that into the DR4. And here the I/O stuff will just pulling the data from the DDR to be shown on the software tools from So from here, that's a simple overview of the data just for this demo. But with the I/O oscilloscope, you can set up different parameters to generate data through the DAC bus. And the same for acquisition. You can use exactly the same demo setup by using I/O oscilloscope, so that will be transparent for the user. Just need to configure what you want to acquire into I/O oscilloscope from the signals you want to acquire on the other side. So that's pretty easy to set up and go into the proof of concept of your application using the TechNES. Okay. So for the porting generation, so what we did for that design is you have all the sources, all the source code from GitHub, from other devices. You need just to identify which evaluation board you are targeting, which analog converter you are targeting, and then that will give you, for example, design some source code for the IATN, for the Zinc virtual scale, for example, for other FPGA solve. You could run also some generation code with what they call the no OS flow, so you don't have any Linux OS running. So it really a matter of choosing a starting point from the analog GitHub, and then that's where simply just update design and update device tree for the Linux, because the Linux system. That's where it became a little bit tricky. So you really need to be careful and know where you are modifying the code. But that's definitely here where you will have some porting activities to do from the code running on an ARIA 10 evaluation board, for example, from Intel, so the ARIA 10 eval kit. That's why we need to do some modification. And here also on the device tree, because the device tree and the root file system from the Linux part, on the HPS part of the ARIA 10, that's where all the configuration in terms of clocking of the Linux converter is entered. That's why we need to set up the different frequency. That's where we needed to downgrade the demo from 10 gigabit sample to a 10 gigabit per second to 5 gigabit per second. But as long as everything here is set up, that's the standard flow. So we have for design, we go through the compilation. The same here for the device tree, that we build all your software binaries, your database, and you're basically good to go to test on the platform. Next slide. Okay. So we have our demo, so we are providing all the demo, all the BSP to run the GSD204 on our TechNES module. Okay, so that's good, so you can start doing your proof of concept. But right now, if you are going to your custom carrier board, you will need to modify the design, so the design we are providing. So as I said, the device tree, the clocking string, the clocking tree, and that's where you need also, you can add, you have two paths. So either you can add your own custom logic, own custom algorithm into the FPGA design, or you can use the application layer on the Linux OS, or you can also go different. You can also use the IO oscilloscope if you want to run more testing. And with the end goal here is to have the proof of concept running on unknown hardware, that is something that you have evaluated, that you have validated before going into your own carrier board. So when you will do your own carrier board, you always have that safe backup, if I can say that. Going to that platform and say, okay, that was working. What I did wrong in my carrier board is it, and that will help you identify if there is a bug. Is it from the design? Is it from the hardware? Is it from our rootkit, the carrier board? So it will save you the precious time during debug phases, and that's why we have provided that demo to our customer to help them having some safety net going back to that design, where they know they can have some golden design, and also in terms of doing some development in parallel, so you can develop your own carrier board with the knife converter, and in the meantime, that the development of the hardware, the schematics, layout, etc., is ongoing. You can improve, you can do more tests on that reference platform. Next slide, please. Okay, so that was for the ARIA 10. Intel, so Intel ARIA 10 module. We know that not all customers are using Intel, so also we are providing that on our Zeus module, what we produce. That is based on Xilinx InfoSafe Plus devices. Same setup, same demo, so I will not go through the same detail. Only difference here is that the two FMC connectors are outside the module for this one, and that's the same. For example, you can take that basic baseboard where the module is located. You can plug your FMC, your FMC converter on one or two of the FMC plus slots here. You can start your proof of concept. And the good thing is, if, for example, that pair board is working, the form factor, maybe you need to change a little bit the size, the feature on it, and you want to directly put in a chip-on approach. You can just put the analog converter, remove the FMC here, put the analog converter. So that would be a really reduced design in terms of time to market, in terms of human resources effort, and also in terms of approach or risk. You can have the proof of concept, modify that pair board. We can also help modify that pair board. And it's basically maybe 2 years, 18 months, 2 years development reduced in like maybe 12, 9 months. So with less risk, and also with a golden reference design that you can go back if there is anything going wrong during the debug of the final pair. So we'll not spend too much time here. So let's quick overview of this module. So as I said, based on module 11, compatible up to Redmi 19 and PSOC devices. So up to 32 transceiver, going from the bottom connector to the carrier board. 16 transceiver at 25 gig on here on the top connector. So it's more with high copper cable connection board to board. We got some media ports. Okay, that's typical from a high-end module that we are providing in our portfolio. Yeah. So same FMC, so if you can just go back to the next slide. Okay, same porting activity, exactly the same. We have the PL side, the PS side, so the FPGA side and the processor side into the MPSOC. Same activity, same approach. The only difference here is we are running the demo a little bit higher. So why the difference here? In the design example, in the DSD framework on our devices, for the Zinc circuits, we are using 2 different PLL. So one is the QPLL, the other is the CMPLL. But with the different split rate, we are running at 2 different frequency range to generate the PLL. So we can't generate the same frequency outputs for that module. Going to a higher speed rate for the MPSOC, so for the V2+, you can run at 10 gig and 10 gig on both sides. So just to explain the difference why we have 10 gig on the ADC and 5 gig on the back end. Same here, so really low power. That's a low power estimator. It's very difficult to isolate the exact consumption of the FPGA, but definitely this design running at 10.5 gig is really low power consumption on using Pascal+. So again, that's something that is high performance with low power. I think that's something that is very interesting. And in terms of resources, also consuming little resources, a lot of RAM, but again, that's not just as simple as going from the analog framework going into a quick proof of concept running the GFB framework into the input perspective devices with our system. So that's for GSD 204B. Next step, we're going to GSD 204C up to 32 gigabit, up to a wide range of frequency acquisition. So that's not finalized yet. The plan is to use the various electronics to FNC cards to play on the electronic devices from various. Same approach, different from the framework on analog devices, which is more mature, more tools. It's the same, but just to provide the GSD 204C to our customer. So a quick explanation. So you can see here, so you see the back for the direct design. So what we did, we are using very small transceiver, of course, going from the 204B to C. Little bit also new feature in terms of clock encoding, 8-bit and bit to 64. It's taking that FMC evaluation board from Riot and put in the same way as the DFT from the device. Same approach. You just connect that and provide all the data layer to our customer to run the reference design and have some golden design before going into the modification and the final data. It's a bit more complex in terms of reference design. So what we did here is we did the feasibility study, also what we need to do next to provide the design to our customer. And just going back to some numbers in terms of specification for the layers, so you can have with the 204C up to 64 gigabit sample per second, open best resolution, fancy range up to 36 gigahertz. For this demo setup, we will run up to 12.5 gigabit per second. That's the speed rate of this module. For the GTY transceiver going down to the baseboard, if we need to go up, for example, 16 gigabit per second, we just need to change the speed rate of the link processors. Using the 16 HY here, the transceiver, still something that is really low power, like what I do, so 13 watts. I will not go into the full detail here about the system, but basically what we're doing is taking the full reference design from Diet and move also, we have a lot of work to do from migrating the microblaze code that is given by the reference design to the PS side of the input using the QRTOS example. And here it just set up the whole design for our customer to have a reference design, reference platform where we can use the FMC and the electronic FMC from various, the just module, the carrier board, and all the software tools provided also by them. That's not finished, just to give you some clue where we are heading in terms of providing GSD reference design to our customer. we are the hardware-based company first, but we are expanding also in terms of providing that solution for our customers before going into a final design.
That's your last one.
Yes. Okay. Now, but the thank you slide at the end. Thank you.
Any questions? From the audience? Ah, time of arrival.
So the B stack has been around for a long, long time.
I think the C is, that's a good question. I don't remember exactly, but I think that's, yeah, that is good. Okay, one or two years. Okay. Thank you.
Okay. Thank you. I think I presume you're trying to find your way back to my slide. Tony. Okay. There's a time of the arrival for lunch. We'll just finish up now. Oh, can you get speed read? Right. Ah, perfect. Okay. Right, so we're just finishing off now. Next slide. So I don't know if you're aware that this is all part of TechWorks or TechNES, which you can see Drew used to run, and I'm really recruiting for these roles now. Our four main things that we run are FPGA frontrunners, which is obviously today's group, and our next one is in July. We'll give you a little bit of detail on that for next time. We run a verification forum where we collaborate on trying various topics of verification. That's both ASIC and FPGA, and also working quite closely with universities to try and bring more students into our industry. So if you're interested in that, you know. There's an RF group that's, I think, started probably just towards the end of last year, kicked off in Cambridge. We were due to have an event on that in Bristol in April, but there's some illness, we've had to delay that, postpone it. That was going to be on 5G. PicoCom, you know, PicoCom in Bristol. And the last one is AIML, where there's a lot of interest in across TechWorks to try and understand a bit more about AIML and how it can be applied and how it can be used in our industry. At the moment, we're talking more about development flows, so how you can build AIML into your development flow. One example is on the verification forum about how you can generate more intelligent stimulus to do coverage closure using AIML. And there's some research going into that. We're trying to put some bids into innovate in Cambridge. And I've got all the information. Not working. So the idea behind FPGA frontrunners is to basically connect people. I think mostly it's FPGA users here, but obviously they're working around to ASIC as well, not FPGA as well. So there is an ASIC community interest in this group as well. I'll just tell you when the next is. Yeah, so the next one is at Leonard on Wednesday the 12th of July. At Leonard Edge. Will be, I think today's experiment went well enough, but we will be broadcasting again. There's a few teething problems at the end, but by the third speaker, went smoothly. Thank you. So thanks to Angela for fixing that. And the theme for that is how to capture and verify requirements. There would be a lot about, but requirements-driven design and verification of traffic standards. And we will be having a third one later in the year, probably around about September, October time, and that will be at Thailand event. And then, oh no, not too quick on that one, sorry. And the other thing, which I mentioned, is there was going to be a 5G event, which unfortunately we had going to do. But it will come back, and it will be at PeopleCom as well, because there's a few labs that we can visit in Bristol as well. I think the university is involved, because they've got a big 5G lab, and PeopleCom has got a big 5G lab as well. So that will happen. Okay, and the design verification forum. So some of you may know that is already. We run an event called DV Club, Design Verification Club, and we run various events. They're all online, and you can register for them. We hold 4 a year, so actually, we'll 2 already this year, but they're usually every quarter. The next one's on performance verification, so how you can verify the performance of your SoC, and then you've got September 28th November in the DVD in terms of topics. We run something called verification forum, verification futures, and that's physical. We run that every year in Reading, and it's both physical and online. And this year we do have an FPGA verification stream where the developers for UVDM and OSVDM will both be presented. So, and there's a main sort of ASIC stream and a separate FPGA stream as well. And that's an all-day event. It's free to register. And we usually get around about 150 there physically, and it might be higher this year, and about 300 or 400 online as well. But that's a big event of the year. And it's free, as I say, it's free to attend. So if you go there, and then we'll send these slides out for you. We are trying to get more students into design verification, and this also has a stream of students that DDoS teach. There's been 2 long sessions, one teaching UVM to students, and very long background in design verification, and also a choice between simulation and formal as well. So there's the student stream as well that runs in parallel. And last year we got about 20-25 students to that event. Hopefully this year we'll get like 50. So it's a good recruit as well. If you want to go and network and find some students. Everyone's always trying to find students. Well, hopefully we're about 50 of them here and 50 students interested in design verification as well. And what we did last year as well, companies sponsored the students to turn up. So I know that, so for example, in Finian and Bristol, they hired a bus, and they took about 8 students in the minibus there, and they had them trapped. I think they recruited to on that minibus ride as well. So there is advantage, and you can just put some money in and we'll get the students there by train or bus or whatever. And then the last one is the EV course, which is again this has come out in verification forum, but trying to help more students into the design verification through that thing is not working. Okay. And this is a verification course that's put together. So TechNES has put together an academy which is aimed at trying to bridge the gap between university and industry. And the first one on this is design verification course. We've run twice now. Each time there's been about 16 students on it. And it's going to run again later in the year. And it just tries to bring them up to speed on verification. And it was put together because a lot of companies will realise this thing. A lot of their senior engineers spend a lot of time trying to bring the graduates or placement students up to speed. And it's quite expensive and also not done consistently. So we put together this course. The TechNES is trying to put together more courses into that academy. But it's struggling. We did discuss FPGA, but there was too diverse a need. We've got lots of people working on different types of FPGA boards, but it's very difficult to find a core service that we could put together. There. We're thinking of doing one at RF, but you've got and possibly AI ML. But if you've got the ideas, it'd be good. And happy the last one. Yeah. The Ben don't worry, you're not you haven't got to give it enough ground for it. So that's it. Thank you very much for turning up. Hopefully see you at Leonard or one of our other events. And I think the food is made timely, and I've been asked if the speakers want to okay to share their slides. Is that the right question? Yeah. Speakers okay to share. Let's share them in PDF form, and we'll probably share the recordings as well. That's all right. So if you've got an objection to sharing your PDF or your video, that's the food made in timely arrival. What time did you want to do the talk? As soon as we can start. Okay, half one. Yeah. So if we go to half one and people aren't ready, we'll do it a bit later, but we'll target half one. And it's just outside in the corridor.
Yes.
Okay. Okay, we'll probably. Okay. But and of course, yeah, thank you very much for hosting and for Leonard hosting. Thank you very much to our speakers, and thanks to Angela as well, who battled the way. And thank you very much for turning up. Thank you. Thank you.
No, that's right. We'll go back. Generate the
Yeah.
No, that's all right. I'll face it. Okay. That's fine. It wasn't. Yeah.
Maybe less true now.
Is it there?